somewhere on the Moodle page. Here it is, time number 1. Some stuff from, you also need, I think, this file as well, one of the questions. Some solutions to MATLAB, solutions for the week 1 exercises there as well. So hopefully you're all kind of up to speed on that. Everybody happy with that? Hopefully you've all had a chance to look at the assignment roughly. We'll need to find a group of 3. It's up to you, you can do it on your own, but you can work in groups of up to 3 people. So are you all working in groups or? Yeah? I think it makes sense because it's not a huge number of questions, but I think it would be a little bit time consuming to do them all by yourself. So I would sort of suggest that you want to pair up. Okay, cool. Any more questions before we launch into the lectures? Okay, just to warn you that you have to upload your solutions to the Moodle site. So you need to do that. Each person needs to upload solutions as well. So even if you're a group of 3, say, you still each in that group of 3 need to upload your solutions as well. And then there's no, if you're late, you won't accept it, the website. Okay. So the deadline is firm in that sense. So you have to make sure that you upload it by 12 o'clock on the 25th. Okay. Okay, I think we were around about here somewhere. So we were talking about graphical models more generally. So we talked about belief networks. We talked a little bit about undirected graphical models, Markov networks. And we were discussing a little bit the kind of representational differences between these kinds of networks. So and this was sort of this language about whether or not whether or not the graph can represent all of the independent statements in the distribution and vice versa, and the various terminologies. And we saw that indeed, not everything can be represented by a belief network, and everything can be represented by a Markov network. These are not the same kinds of things. And I also wanted you to bear in mind that there are some kind of, elephant traps out there, probability. So, we've seen a couple already, but maybe, I don't know if you went through this last time, but this is another one. So I think this, it seems very reasonable to, if A is dependent on B, and B is dependent on C, then you might think, it would be very reasonable that A would be dependent upon C. Because if you sort of write this down as a, say, belief network, you might have something like this. A is dependent on B, suggests there really is a link here between these two variables. And B is dependent upon C, kind of suggests there's really a link here, right? And you expect possibly then this kind of, some kind of transitivity, things would sort of, this is dependent on that, and therefore, if I change A, surely C is going to vary as well. This would propagate down the chain. You would expect that. It's not true. So these two statements do not imply that statement. Remarkably not. And this is an example. So I've written down this distribution here. Okay, of the 3 variables. Actually, it's going to be a chain for this form. These are the distributions for the discrete variables. So A's got 2 states. In this case, B has got 3 states. C has got 2 states. So these are the distributions. They all normalize to 1, and they are negative, so that's good. And if you do this, if you work this out, you'll find that in fact A is independent of C. So how would we show that actually? How would we show that A is independent of C?
The product.
Yeah.
Probably is a product.
Yeah, we'd have to show that so A independent to C means that P A comma C is equal to PA times by PC. Right? That's what we need to show. And we need to show that in this case numerically. Right? So you can either work this out by hand, right, which is not that complicated to do, or you could work it out with a computer, assuming the arithmetic in the computer is going to be carried out correctly. And so in this case, there's no real concerns about that. These are all just, rational numbers, so we're not going to. There's no computational real problems there. So you were comfortable you could do that? You could work out and show that indeed then this joint distribution would factorize this way? Yeah? Well, do you want me to show you this? Who wants to see this?
Example, yeah, sure.
To see an example. Okay, this might take a little bit of reconstructing then, just bear with me. That's it. Well, let's do it from scratch then. So I don't seem to have a. This is going to be tricky, isn't it? Let's see if we can do some real time editing here to apply. So let's try to define this, right? Let's say PA is an array.
David, can you move the whiteboard down slightly, or move something else up? Thanks.
Sorry. So we're going to say PA dot the variables. We're going to do. Let's call variable A number 1. Okay. Let's say PA dot table equals 3/5 and 2/5. 2. Okay, do stop me if I do anything silly. That's the first one. There's a PB given A. Let's do another one. So PB given A is another array. Say the P given A dot the variables are going to be. Let's say B is variable 2. So they're going to be 2 and 1 for PA. And PB given A dot table is going to be 1/4. No. Let's get this one way around actually. I might get this wrong way around. And maybe it goes row wise and not remember. Let's try to do the first row. So 1/4 15 over 14. 112 1 over 8. And 2/3 1/2. 2/3. Okay, so we got that right. That table should sum to 1. Right? So let's do sum B given up. Yeah, so the cost. Well, that's so just define the PC. P is an array. Actually, we'll call that variable 3. PC dot the table is 2/3, 1/2, 5/8. Okay, sum. Oh, so I should build up this C give B. Okay, so that's good. So now the joint distribution. Look at the joint is the multiple, is the product, right? It's the multiple of PA, PB given a PC. Oh yeah, because PC is not this. It's a variable 3 and 2. Okay, so the joint. Okay, so it's 1, 2, 3. So if that's correct, we just make sure that the joint is indeed a distribution. Okay, so this is the joint is a distribution over the variables 1, 2, 3. It's a 2 by 3 by 2 table. So what we need to find now is the marginal distribution of PAB. So PAB is the sum of the joint over variable C. Sorry, PAC.
Sorry for the question.
Yeah.
You check that this is this distribution, but this doesn't sum to 1, or? You check that and then you got some numbers which aren't ones. Or the sum of all of these values is 1, or?
But let's say T is equal to the joint dot.
I think you just weren't seeing all the numbers because they were off the screen.
So if we do the sum of T. MATLAB's a little bit, we'll do the sum of this. So right. What's the sum numerical? Okay, so PAC is the sum of the joint distribution over the variable 2, which is this B. Okay, so it should be a distribution over A and C now. So what we need to show is that, let's find the marginals PA and PC. So it's a little bit bad notation from before. So let's say PA. Well, we already know what PA is actually because it's given by the first table. Let's say PC marginal, whatever. PC equals the sum of PAC over A, which is variable 1. Okay, so now what we need to show is that the product of these two marginals, so MC times by PA. Let's call that 10. Right, that this actually is equal to PAC. Because then we'd have frustrating numerical distinction here, bit difference. But these are, if I were to write this out without some kind of rounding, you would find that these are exactly the same. Let's see if we can actually address that template table. So that annoying one, these are the 1,2, right? Minus PAC dot table. Yeah, so there's no difference. For some reason MATLAB plots it differently, displays it differently, but it's exactly the same number. Okay, so this I don't know about you, but I find this personally quite a sobering example. It's very, I think it's very non-intuitive, I have to say, personally. And there are many such kinds of things. Before we saw this thing about conditional independence of variables, so of course conditional independence doesn't mean that you're marginally independent, etc. So here's another quick one for you. What about, let's say that A is independent of C. No, let's say A is in B, and let's do another one. Sorry. Let's say A is dependent on C, and B is dependent on C. Does that mean that A is dependent on B? So here you see the kind of A and C are linked together somehow, and B and C are linked together in some sense. They're dependent. So you might think therefore that it's natural somehow that they are both A and B are also linked or dependent in some way because they're kind of commonly sort of linked through C. Do you think that follows?
What's the difference between this one and the one above? It's this. You only place
This is
C.
a B, that's a C.
Yeah, I mean it's the same.
No, it's not.
Same idea.
It's not exactly the same.
No, I don't think so.
One's a chain of dependencies, the other one's a fork.
Yes.
Can the first one, if you put it in a base network, it
Yeah.
would be like A
It's
and B?
It's this, actually, the first one.
It's this one?
Yeah.
But if you're gonna read this as a...
This one is this one. This one is a different one. I mean, it helps to know, obviously the solution. It's useful to know, to picture what the graphical model corresponds to here, and it's obvious. We have that, but it's what the solution is, but it's the fork, if you like. Well, that's one way to represent it. But anyway, can we have a vote as to whether or not you think this is true or not? Who thinks it's true? One. Only one person thinks it's true. Two. Only three, four. Only that few people think it's true. Really? It's only 4 people think it's true. Who thinks it's false? More people think it's false. Okay, and who doesn't think? Okay, so the majority are not thinking. Okay, guys. Well, it's not true. By the way, these were exam questions last year. To wake you up for those who are not thinking. So you could represent, you could have a belief network like this, right? You could say from this belief network, as long as we don't choose some trivial table dependencies, it's clear that A is dependent upon C, and B is dependent upon C, but marginally A and B are independent. Right? So clearly, in this case, we would have A is actually independent of B. So this one here, this is kind of tricky things, right? So in this case, this marginal independency follows, but it's very difficult to graphically represent dependencies or to have implied dependencies generally with graphics. It's we're representing independencies, but dependent statements are kind of difficult to follow through from the graph itself. Right? I mean, they're kind of things. Yeah.
I've got a question. If B is dependent on C, and this is if and only if C is dependent on B, isn't it? So you can change the order of
Yes.
B and C. Then you can rename C to be B and C to be B to be C and C to be B. And so why is the second example different than the first example? As
Yeah, I don't
well asked. I think from a mark point of view, it's the same, isn't it? So you just rename C and B.
Yeah, true.
There's a problem with the notation.
Yeah, because it's
A and C are dependent. You don't say which is dependent on which.
No, that's true. That we can switch around. That's true. So let's. I see what you mean. So if you switch B and C, you can have that. Yeah, that's true. So I agree. In that sense, it's true. But if I were to, in a sense, there are. Yeah, that's true. But this example is a little bit kind of more, in terms of a graph, at least, is more obvious why A and B are independent. Because clearly, you just sum over C. But in this case here, it's much less clear why. If I gave you, I said, the distribution which is underlying these three variables has this structure to it, it's much less clear why A is independent of C.
I think this graph does not say so, though.
Neither graph
this linear
says.
thing does not encode this independence, right?
Correct. That's what I'm saying. It does not encode. So you have to be very, very careful with stuff, right? So these are, nice questions for you to ask in an exam, in a representational kind of understanding. Okay, so the story here is that local dependence, if you like. So you could have indeed tables, which, as we saw in this example, which indeed are expressing dependence, and it doesn't really guarantee that the path connected variables are going to be dependent. There's no such guarantee. And in general, graphical independence does not imply distribution independence. Sorry, it does imply, but graphical dependence does not imply distribution dependence. Yeah. Okay, so let's move on to a new topic. I'm going to talk about another kind of graph now. So factor graphs. But these are a little bit kind of not so commonly used in representing modeling sort of situations. They're really, I think, more commonly used is for computational purposes. So what is a factor graph? Well, basically it's a thing like this with variables and these factor nodes. I'm just representing these as little square boxes. And the semantics is that this whole graph means that you take a product. So wherever you get this thing, you look at the variables which it's connected to, and you have a potential on those variables. Okay, so here, we've got a function f4 of D and E. We've got a function f3 of C and E. We've got a function f2 of D, C and B, and similarly f1 of A and B. We take the product of all of these potentials together, and that will give us our distribution. Actually, factor graphs are they're not necessarily distributions. They can just be non-negative functions, actually. You don't really require them to be distributions. And most of the time in this course we'll be thinking about them as distributions. Okay, so this looks kind of similar to a Markov network, but it's not quite the same thing. So on the left, we have a distribution, a factor graph, on A, B, and C. And in the middle, we have another factor graph on A, B, and C. So, but that's kind of a different structure to it than the first one. This is 5AB, 5BC, 5CB. And if you were to say, well, I want to represent A as a Markov network, but some function of three variables. So all you could do is say, well, it's a clique on those three variables, and it would have to be A, B, C. And similarly, if you want to represent B as a Markov network, again, it's just some function on three variables, and it has to be again represented by C. But in terms of a Markov network, you cannot distinguish between A and B. They both have the same Markov network representation. So the independent statements are the same, actually. Neither of these graphs really A and B are representing anything different in terms of independencies, but they do represent something different about the functional form, or the way, the parameterization, if you like, of the distribution. They're not the same parameterizations. One is more constrained than the other, but they are equivalent in terms of their Markov properties, their independent statements. Okay, so this is something that, it's kind of a little bit strange again, but it's kind of useful to think about this Markov network, this factor graph, rather than Markov network. And the reason is that when we're going to do the computational devices soon, we don't really want to worry too much about whether or not the original representation is a Markov network or a belief network. We're going to try to sort of compile everything into another representation, which will carry out all the computations in that new representation, and that will be the factor graph. You don't have to do that, but people kind of like to do that. I feel duty bound to tell you that's the way. Okay, so move on to the next set of lecture notes. So now we learned a little bit about these graphical models, okay, so the distributions, and get some idea of what we can do with them. But now we want to not have to do these computations by hand anymore. We're going to try to get algorithms to do inference for us. So what do I mean by inference? I mean things like, what is the probability of a variable given, say, conditioning of the other variables in some states? What's the most likely joint state of distribution, say? What's the entropy of a distribution? What's the probability, say, some example is in a particular class? What's the probability the stock market will go down tomorrow? These are all inferential questions. So what it means is that we use the distribution, if you like, as a kind of an oracle, which we will query to answer questions. That's the idea of inference. There are all kinds of inferences that we could demand, and that's. We're going to focus actually here on some specific, usually a couple of kinds of inferences. Things like, most likely state of distribution is a good one. What's the marginal state of distribution? That's another one that we also focus on. But the difficult thing with this is that actually inference, in some sense, is really hard. Typically, not always, but typically, it's a hard thing to do. There are only very special cases where inference is easy, and we're going to do the easier ones now. Okay, they're quite useful. They're very, very useful, but generally, it's a nightmare in some sense. Which is really why probability is a kind of Pandora's box in some sense. It's a great modeling tool, but generally we are struggling to do inference. So the big thing is it's all about computational efficiency, and it will turn out, by and large, that for singly connected graphical models, inference is going to be easy, by and large. For multiply connected graphical models, by and large, inference is going to be hard. It's not totally, strictly correct what I said, but as a sort of rough idea, that's the. So we're going to look at a specific. We're going to use these factor graphs now to represent distributions, and we're going to think about some inferential questions and factor graphs. So what I want to do is I've got a distribution over these four variables A, B, C, and D. So that's my factor graph representation there. I'm going to assume that these are binary variables. And let's say I want to find out, infer what is the marginal distribution P of A. So to get that, I'm going to have to sum over the states of variables B, C, and D. Okay, and I'm going to assume that maybe somehow that this thing is correctly normalized. I'm not going to worry too much about the normalization constant. So maybe F1 contains normalization, if you like. It doesn't really matter too much. Okay, so to do that, I can plug in. One way to do it would be to plug in this factorization like that, and say, well, I just have to carry out now for each of the 8 states of these variables here. There are 2 to the power 3 joint states of these variables. I could for each of those 8 states, I could calculate this product and then sum them all up. So there'd be 8 terms in that summation. Each term would itself be product of 4 numbers. Okay, so there would be 8 sums in that case. So there's another way to do it though, right? So we could say, well, this thing here, we're not really exploiting the fact there's some structure to this distribution. Maybe we can exploit that structure to reduce the computational effort. So you could, for example, attempt to distribute this summation over this product in some way. So for example, you recognize that here, these terms don't depend upon D at all. So effectively they're constants to D, so you could actually distribute the sum over D, you could bring that inside and put it into here. There's nothing before that depends upon D. Okay, so when you've done that, you can similarly distribute C down to here, and then you're left with B. You cannot distribute B any further. In that case, you've got to do one sum here, and then you have to do another sum here, and then you have to do another sum here. Why do I say 2 by 3 sums? Yeah, because each sum is containing sum over 2 variable states. This is fine. So in this case, there are actually 6 rather than 8 summations to carry out. There are actually less products as well, which is good. Now, one way to think about that is to say, well, when I've carried out this summation over D, whatever that is, this is some function now with the variable C, because the dependence on D is gone. So I could write that and say, well, whatever it is, I call that, say, mu of C. And I could, just for notational purposes, I could say, well, that's kind of, that thing is a result of passing, if you like, or eliminating the variable D. It kind of, in some sense, it's like eliminating the variable D and passing the remaining information to variable C. So kind of, we could represent that as a sort of as a message, if you like, from D to C as a function of C. And once we've carried that one out, this thing now is some function of C. So I can sum this over C, and what we'll be left with is some function of B here. So I could write that as a message itself. Now, from C to B as a function of B. Okay. And similarly, I then carry out the final sum over B, and that's a message from B to A as a function of A. Okay, so this is a kind of what people like to call a message passing scheme. It's really also dynamic programming. You could also view it in that way. Computer science is the same kind of idea. Like you're just recursively breaking down a problem. Okay, so that's good. So that's nice. I mean, just to maybe hammer this point home a little bit here. You may think this is not really a big deal, right? You just reduce it from 8 sums down to 6 sums. But let's imagine you had a much longer chain, like A to B to C to D, etc., all the way down to, say, Z. Right? So let's imagine now you wanted to compute, what is P of A from this. So you'd have to sum over B, C to Z of this factor graph. Right, so how many terms would there be in this summation? If you were to do it in this naive way. Any more than 8? Any advance on 8? No? Less than 8? 10? 9? Who has a guess?
2 to the power of 25.
Okay. 25. 2 to the power of 25, right? I don't know how big that is. Did you see what MATLAB says? it's not that bad. Could probably, maybe, it might take you a day or so on my laptop, I'm not sure if you could do that. But you get the idea, right? It's exponentially growing, the length of this chain, okay? But if we were to do this by message passing, okay, there's going to be reduced to what? Order, how many summations?
2 times 25.
Yeah, it's going to be 2 times 25, roughly speaking. So we're going to get reduced from, exponential to linear. This is great. But this thing here is just really expressing the fact that if you have a joint distribution over many variables, in general, computing some kind of margin or something like that is exponentially bad. You're screwed. Absolutely screwed. There's nothing you can do in general, right? However, if you do have some structural property, like for example, in this case it's a chain, a factorial chain, you can reduce it dramatically down to say linear time. Right? And in this case, we had a very simple singly connected chain. So this is huge. So you can imagine, computer scientists and people, they're beavering away, not worrying about, they're not bothered about these kinds of generic structures. They're all trying to find tractable structures computationally for which inference is feasible. That's the whole game. That's the whole reason we have these graphical models. Otherwise, we wouldn't need to worry about this kind of stuff. Okay, so if you want to compute, say, something, this is just the same as before, but you can also compute messages in other ways. You could, make a message going the other way along the chain as well, but that's how you can think about messages. So let's imagine you want to compute another marginal inference, like say, what is P of C? Okay, so in this case, you could distribute D over to here, so that would give you a message. Here you have to sum over A, so you see that A only appears in here, so you could carry that sum first. So that's like basically a message from A to B. And then we've got a final sum over B. So one way to think about that is to say, well, I want to calculate this marginal here, this variable. So I have to kind of pass information from this end of the distribution chain towards C, and pass information from this end towards C. Okay, and then I need to take the product at C of these 2 incoming messages. So now, this is really kind of enough to understand, how to do message passing, this marginal inference on a chain, right? You can see that all you need to do is that, the message is going to be the current factor multiplied by any incoming message summed over the variables from the incoming message, and that's it. That's the whole thing that you do, and then you just pass messages recursively from the ends inside to wherever you are, and take the product of the messages, and that will be the resulting proportional to the resulting marginal. Now another thing to say is that I kind of finesse this point about the marginal, the normalization constant of A. So I said that I don't really care about it, but let's say you do care about it. Let's say that somebody indeed has given you a factor graph and say, well, it's of that form before. Okay, so something gives you this, right? And they say that they don't tell you what the normalization constant is of this distribution, but they really care about calculating P of A. Let's say there are 2 states of A, and they really want to know exactly what that is, including the normalization of A. So what I've just told you is how to carry out these sums, but I haven't told you how to get the normalization constant of A. So far we only know A will be proportional to some number. We've got some resulting computation now as a function of A. Right. So how do I figure out what is P of A? I don't know the normalization constant. How do I get that? Let me give an example. Let's say, so f of state 1 is say 23, and f of 2 is 27. What is P of state 1? Sorry?
0.46.
0.46. Well, can you give me as a fraction? Well, 46 over
42.
Okay. That's all right. I mean, I would prefer 23 over 50 personally, but it's a simplified fraction. So why do you say that?
Summed over the two, 1 and 2,
Yeah.
two factors, and then divided both with the f of 1. So
Yeah. So P of 2 would be
27 by 50.
Is that obvious? Gosh, you're so quiet, you guys. Don't forget, your exam will come next year. And you will not see me. I'm here for a few weeks only. You will not get any help. If you're struggling or don't understand it, this is your time. There is no second chance. Today is the only time I will explain this in your life. Okay? Make use of my time. And your time, of course. Is it obvious?
Yes.
Who doesn't understand this? So if I asked you to formally prove why this procedure is correct in an exam, what would you say? Next question. I mean, it's obvious, but we need more than obvious, right? We need like to show it, prove it, if you like. Why is it true?
If we remove the proportionality,
Yeah.
I put a constant and then integrate.
So let's say constant C, right? Times by, yeah.
And then we do a summation on.
Okay, so let's say sum over A, P of A is equal to sum over A, C times by F of A. Next step.
The sum is equal to 1.
Okay.
C.
Great. Now, let's do a slightly more complicated example. So the previous one is kind of easy, right? Just moving messages along a chain. But we could also look at a kind of more complicated, singly connected structure. This is a branching tree, right? It's a tree. It's got branches. It's still singly connected. Now I can write down, say, the factor graph here of this distribution. And let's say I want to compute the marginal P of A. So algebraically, we're in the same game as before. We want to try to distribute the sum over B, C, D, and E as far as we can to the right of this as far as we can over this product. That's the trick that we want to try to carry out. So, as usual, you can say, well, you could look at this thing and say, well, I can certainly sum this one over E, so that's an easy one. That's going to be some function of d. I need to sum over all kinds of other things. D would be a little bit tricky to sum over directly. I can't, because I've got a d here. And c is also kind of, it's in here. So it doesn't seem that there's a lot I can do except for sum over jointly c and d now, this whole thing, which is a function of b, c, and d. And then I could sum over b of this product here, and that would be some function of it. So we could represent that as some sort of thing where now this is effectively some message towards d. I've got some kind of message from d here, just a kind of a single term, if you like. And then I've got this factor c, which I could also write, if you like, as a message from f. Yeah, this is a bit weird actually, but maybe we'll come back to that. And then these two get producted together, these messages multiplied by this one here. You get a sum over the b, c, and d to get a new message towards a. So the kind of the picture here is that both branches, so this branch here, we could carry out this message from this variable to this one, right, independently. That could be carried out. But then when we get to this branching term now here, between the product of these incoming messages in this branching node, then sum over the two variable states, the variable states of these two variables, in order to go beyond this branch to get to b. And then we're back in the sort of singly connected, simple branching structure here from b to a. Okay, so the main thing to just recognize is that you can again carry out local branch messages as per usual in your message passing procedure. When you get to a branch, you take the product of the messages of the branch and then continue summing over the states of the variables which were in those two branches, or however many branches you have, and then continue as usual. And this sort of thing here is just a kind of a notational device to make sure that when we talk about the algorithm as such, that this kind of makes sense in some way. It doesn't really matter. The only thing you really need to understand is this intuition. That's everything there is. The rest is just however you like to write down the algorithm. It's just there are different ways of doing it. Okay, so the point is then that what that means effectively is that any singly connected structure, you can carry out marginal inference for it, at least in this sense, easily. Right? Within these binary or discrete variables, we're not going to have a problem carrying out inference for a single variable. It's going to be essentially linear time gain in the size, the number of variables in this graph. Okay, so I think it's time for a break, right? Is it right? No. Sorry, I've got the wrong time, haven't I? Let's have a break in half an hour. That's good. So that's bad, isn't it? Because now you're all thinking about coffees. All right, so one way to write this down is an algorithm is the following. And bear in mind, again, there are different ways to write this down. They're all mathematically equivalent. So we define two kinds of messages: factor to variable and variable to factor messages. So if you've got, say, variable v here, and these are factors f1, f2, you can define a message from v to f, from going from here to here. Right? You just simply take the product of the incoming messages, f1 to v, f2. This is called a variable factor message. Okay. And then there's factor to variable messages. So this one here is factor to this variable. Basically, you take the product of incoming factors here, and you sum over basically these variables here, multiplied by this factor. So this is the factor f. You take the product of the incoming factors, and you sum over all those variables which are not here. Okay. That's the factor variable And the marginal is given by just the product, it's just a portion of the product of the incoming messages. Okay, so this is one way to organize the algorithm. And there are many other ways to do it. So this thing sometimes is called belief propagation. That's probably more the original notion for it. But of course, I mean, this thing, you know, everybody who sort of thinks about this for 5 minutes can write this out, or, you know, a version of this algorithm down. It's kind of clear, right? Even though this was considered a military secret from the 1970s. So people have been using these algorithms for all kinds of, you know, complicated purposes, and in engineering particularly, and this was considered a military secret. But it's not a big deal. So you'll find that, you know, people probably in computer science would have got the same algorithm. If you look at the old papers from the 1970s or 60s even, and they would call it sort of dynamic programming, a version of dynamic programming. But the statisticians will call it something else as well. But now we are coalescing around this phrase, the sum product algorithm, because basically you're distributing the sums over the product. Now, what if you want to do another kind of inference? Let's imagine we want to compute, say, the most likely state of distribution. So we've got, say, a vector graph again. Let's say you start off with a simple one. And you want to find the most likely state of the variables A, B, C, D jointly. Okay, so that's that setting of the variables A, B, and C which jointly maximizes this whole thing. This is distinct, by the way, from calculating the marginal, say, P of A, and finding the most likely state of P of A. Finding the marginal P of B and finding the most likely state of P of B. It's not the same thing. This is the joint most likely state. So if you think about this in terms of tables, you know, we have here a 4 by 2 by 2 by 2 by 2 array, which have 16 states in it. We're going to search all those 16 states in this array and find that single one which is the most likely. That's the highest value. So what we need to carry out is this. Again, you know, we need to do this maximization. So we could, you know, you just enumerate over the 16 states. That would be one way to do it. It's a flat thing, but again, that would be exponentially bad. But we can also distribute again this max actually over these elements. That's doable because this f are assumed to be non-negative. If it didn't have that, we could not distribute this max. So this only works for potentials. This is not generally true in mathematics. You cannot distribute this max generally. But if it's positive, you can. Or non-negative, you can. It's okay. So similarly, we just again exactly the same structure as before. The distribution is the same with this operator, and we've got the messages as before. The only thing that's different is that where we had a sum, we've now got a max. It's the same. And again, of course, it was true for the non-branching. For the branching structure, so we just define again messages. We're taking in variable to factors. It's the same as before. Variable to factor to variables, the same as before, except where we had a sum is now replaced with a max. And everything is as before. And the most likely, most probable state of the joint distribution is just given by that state of the variables, which maximizes all of the incoming messages. So what I mean by that is that, let's imagine now you've computed, say, a message into C, right? So you've computed this maxes this way, say, and you've got the maxes that way. Then you take the product of these incoming things. There will be some function of C, and the state of that product multiplied with these incoming messages will be the one which maximizes that product. Will be the most will be the state which actually is most likely for the whole distribution. See what I mean? So you take the.
Can you give an example?
Yeah. So you take the. You have an F2 to C. So that's for the C variable, right? Now we take, if there's two states of C, we evaluate this for the two states of C. We find that state which is the most likely. So we find that has the highest value. So we find that state which maximizes this. So we call that C star. Okay, and we do this similarly for A, B, and D. And we end up with a set A star, B star, C star, and D star. Okay. And my claim is that this state, this joint state, is equal to the argmax jointly over A, B, C, and D, F, the original factor. This is a kind of interesting thing, right? That essentially what we are doing is now these messages which are passed locally, we just take the max of a local product now. But actually the state that corresponds to that maximization is equivalent to the max of the joint distribution. Because effectively the reason is because we're allowed to distribute this max over the various times. Okay. So that's cool, right? So now you've got two algorithms, or one algorithm just with a slight modification, which enable you to compute marginals and joint maximizations over all singly connected structures, at least for, say, these discrete variables. So that's very, very handy. It's a big tool that you can use to solve many other problems. Okay, so just a couple of general statements. So this, like I said, this is sometimes known as belief propagation, or other kinds of terminologies for these things. The physicists have their own terminology, and this thing is everywhere, right? Every engineering, statistics, computer science, physics, chemistry, they all have this algorithm with a different name. So that's the nice thing about graphical models, is we try to clean up all these things and say, well, actually, they're all just instances of the same algorithm. Okay, so yeah, I should say maybe before that if you go back to, say, this simple kind of picture here, actually, you don't really need two kinds of messages. You don't really need factor to variable and variable to factor messages. You can just do directly variable to variable messages. It's possible to do that simply because actually all that's happening is that you're just eliminating a variable at a time. Now the reason for this deduction of variable to factor and factor to variable messages is simply to deal with the branching case here. It's not possible to think here so easily about just kind of variable to variables because of the two branches. If we want to do computations distinctly, we need this kind of concept of these two kinds of messages, and that's why if you go back to the literature, for example, Pearl's belief propagation, again you'll see there are two kinds of messages. And indeed, if you were to yourself, you say, well, I don't care for this factor graph representations. I want to make my own. You'll still find that whatever you do, however you decide to write it down, you'll require two kinds of messages because of this branching situation. So, but these are not required if you have a non-branching tree. You can just get away with direct variable to variable messages, and we'll see an example of that. Okay, so this is cool, right? So you might think this is really nice, and maybe there are many other kinds of operators, not just summation to maximizations, for which you will be able to distribute this operator over this product. And there are actually, and I don't know much about this, but there's a term for it. So maybe those of you that are more algebra than me will know structural properties of this. It's called a semi-ring, apparently. So if your algebra satisfies a semi-ring property, then you can do belief propagation or dynamic, whatever you want to call it, you know, sum product dynamic programming on the corresponding singly connected structure, and it will work. So in other words, if you have a semi-ring structure algebra, you can reduce the computation to linear time over exponential time in singly connected structures. And indeed, this is used. You know, there are. So in other words, you know, you shouldn't necessarily think about this as a probabilistic issue. You know, there's nothing here. We're not in forming this belief propagation or this, you know, these algorithms there. The only thing we've exploited is the non-negativity of these functions f. That's all. They don't have to be distributions. Okay, and this is a reason why you'll find this algorithm used in many, many other cases where they're not even talking about probability. In many other branches of science, there's no mention of probability, but they still have the same algorithm. Maybe you're doing optimization, for example. You just got some function to optimize. It's got a singly connected structure to it. You know, there's no probability distribution there, but you can still carry out belief propagation. Now, if these things are multiply connected, it's much more complicated. So, the reason partly is that if you think about, let's go back to this one here. Naively, all we're doing here is that we're starting from some end of this chain, and we're kind of biting off a variable at a time. That's all we were doing, right? It's a variable elimination. But if you had a kind of a multiplicative structure, say something like this, here, you know, where do you start to bite off the end of this structure? There's no edge. So you cannot begin anywhere. That's one reason, if you like, that there's no way to formalize, or you cannot carry out message passing with this structure naively. So you could say, though, well, I don't care, because if I go back now to my max product algorithm, for example, these messages here are only defined locally. So what it means is that this guy, I can define it. You know, I could say, well, here's a variable. Here are some incoming things. I can define then a message from here to here as a function of the incoming thing. I could define a message from here to here as a function of the incoming thing. And I could do everything, right? So I can define these messages. They're well defined on multiple connected structures. Okay, so you could say, I recognize that in the beginning, when I say, you know, in this singly connected structure, there's an end, so I can compute the initial message from the edge node inside correctly. Here, I don't know, I don't have any edge, I'd have to start somewhere. I could say, well, maybe I'll make I don't know therefore what that message should be from, say, here to here, but I'll make a guess. I'll just initialize it to something random. Or 1, whatever it is, I don't care. I just said, you know, some random initialization, and then I can run the algorithm, right? I can, you know, whatever, even if it was wrong, it could still start defining messages and propagating them around this structure with my fingers crossed that this means something sensible, right? And people do that, actually. So. Again, this is called belief propagation, typically, but it's the implement or the application of belief propagation on a multiply connected structure, and it's just the fingers crossed. You know, if you're lucky, it will converge to something not far off the right answer. Okay, and one way to think about it is, if this structure, this say loop here, were very, very long. Let's say I had many, many more variables in this loop. some sense, how does the algorithm recognize or sense that this is a loop? Well, it senses it's a loop because if he were to change this variable here, it would eventually propagate around such that he would feel some kind of reverberation, if you like, of the change here. This change would propagate around the whole of this chain, and would come back to this point. Right? It would still change. So if I change A, it will have some change upon D, which will again change A. But if this is very long and these connections are not pathologically strong, this kind of effect will be weak. It will become weakened by the length of this chain. So maybe if you're lucky, it even decays exponentially quickly, this dependency. So what that means is that if these chains, so intuitively, if these loops are very, very long, numerically, really there's no distinction between a tree and this loopy structure. And in such situations, you may expect that this application of leaf propagation to loopy structures like this one, this multivariate case, will nevertheless produce a reasonable result. Okay, so you can kind of formalize that. People work on these kind of things to try to understand, under which circumstances would the application of leaf propagation give an accurate result. But it's a very difficult branch of mathematics and computer science, but people do attempt to understand that. Okay, so maybe just to say a little bit more about that, actually, this application of belief propagation to a multiply connected graph actually was a bombshell in science. I mean, science kind of obvious, but people in information theory have been trying to solve problems there for a long time, since the 1940s, in terms of passing messages over channels and doing the decoding. And it turns out that you can write the decoding operation as inference on a factor graph, which is loopy. It's multiply connected. It's very large. You've got many thousands of variables in it. And if you were to carry out the operation correctly, it would be exponential time. It's impossible to do it. But if you run belief propagation on that multiply connected structure, provided you set things up correctly, it always converges to the right answer. In fact, it's never been observed not to correctly converge. And this was an absolute revolution 15 years ago. It's essentially solved one 50-year-old, more than 50-year-old problem in science. You're able to do things now which were thought inconceivable 20 years ago. Again, it's always with a slice of cake. Actually, the algorithm was already thought about in the 1960s by a clever student in his PhD thesis, but the problem was that they didn't have enough storage on computers in those days to actually run the algorithm, so people forgot about it, unfortunately. But there you go. It came back with Avengers. And now, actually, this algorithm will be used in all the next generation of all error-correcting codes, all electronic devices, your mobile phone, your PC, all of them, interstellar communication, whatever it is, interstellar, interplanetary, it will all be done with this algorithm. It's that big a deal. It's huge in science. Because of that, when this revelation came along, every other branch of science was thinking, well, maybe we can do the same. Maybe we can solve our problem in a similar way. So people have been, the last 10 years or so, everywhere you'll see now this algorithm is absolutely everywhere. Every branch where they have a multiple connected problem, they now have a go at seeing the belief propagation algorithm. Okay, so we'll talk about this how to identify singly connected structures by cut-set condition in a minute. What about if the operator is not a semi-ring? It's operator algebra. Well, it won't work. So here's an example. You might think this is a new operator. It's a max sum operator. It's going to max over some variables and going to sum over others. So you might think that this max sum operator is you're good to go with this one, right? Because the max works okay and the sum works okay, but the max sum does not work. This is not a semi-ring algebra, and I'll leave you to think about this. But the statement here is that the max of a sum is not the same as the sum of a max. And this is the essential reason why you cannot distribute this operator in any reasonable way. It doesn't work. It's not a semi-ring structure. So this is something that you need to be a little bit careful about. But again, we will not come across this too much in this course, but there are some classic examples. One very well-known one is trying to compute things like the most likely state of a latent variable structure, latent variables in a latent variable structure. Actually, it's not tractable, even though the graph can be simply connected. So there are some tricky things to learn. Okay, so cut set conditioning. What is that? So this was an old-fashioned way to get around this issue of multiple connectedness. So here's a multiple connected distribution, and we want to run, say, some singly connected inference algorithm. Like, say, we want to compute the max over A, B, C, and D of this, say, product here. Well, we could distribute, say, let's say we fix A, and then we do the max over B, C, and D of this thing here. Now, if we fix A, this is just actually a singly connected structure, right? It's effectively, what we're doing with fix A is we're freezing these kind of terms here, between block A. The remaining of the distribution, B, C, and D, is singly connected. So what that would mean is if I were to say set A to state 1, I could actually carry out Boolean propagation. I could do message passing over this singly connected structure forward to fix state A. And then I fix A to another state, and I then carry out, again, another message passing. And I can do that. So this is the cut set. So basically, the set of variables which cuts the graph, such that the remaining graph is singly connected, is the cut set, a cut set. Okay? And if the complexity was exponential in the cut set states, I can then carry out this kind of inferences, with marginal or max inference. Okay, so this is another way to think about some of these questions. So certainly there are, if provided that you can identify a cut set which has got low size, you can carry out tractably marginal or max inference using this message passing. Yeah, makes sense? Okay, we're going to have a break now. Let's meet back at 22.
Got some reading to do. Which one that is one for me?
Some mornings just weren't worth even trying. I wish there was a big flag at the end of the day when you woke up. Like, don't try anything complex this morning, it's not going to work. It's a much easier morning if I may.
Don't even bother waking up.
Yeah, well, that flag is often one. It's often that I just don't believe it. Make a run to it.
Okay. How long is
how you use it.
Encourage things to be the same stage how they actually
Well, first of all, the icing of itself is a more the bolts condition, which is the general condition, so it has some distribution of So what you might do is you might say, well, I might have a collection of data. So I might say, collection of context for these are observed variables. This might be line. Yes. Yeah. So you have a separate collection of variables. And what you might like to do is say, well, I want to fit this distribution, this form, to this set of data. So in other words, I want to randomly draw a sample of distribution. I don't understand it. These look like one of these. This is very much general. Actually, I understand. So what you do is you then you just try to set these weights. Such that you say, I want to set the weights, I want to find the maximum of the weights W to say maximum sum of data or the probability say, what's the probability of generating is. This is a function.
See the mobile phone line,
So you might say, well, maximize say,
not sure.
for each observation that I've got.
Can't see it down there, no.
Maximize
Drop it down there.
What I've done is actually, that's interesting because what I could do now is say, well, actually,
I'll have a look in a minute proper.
What platform is there?
HTC.
where I say, you tell how it is. But maybe you say, I have some things I don't know. Let's say I don't know some mistakes. What I could do is say, I could say, well, given that I'm observing, what is now, given that I know W, what is the most likely of the unknown ones of this, given the observed ones at W?
So this actually is a lot of complication of image process.
Yeah.
So this is character recognition. So is this what it is? It's like basically
Just
train
like
it with a
fill in.
bunch of examples of A, and then you show something that tells you how likely is it that's an A.
Exactly. Maybe I can try to show you an example of this. The problem is that it's very hard to do this. Actually finding the W is maximizing
Normalizing it.
is really, really tricky because it requires, you take this thing here, you need to know what Z is. And that Z is impossible to get. So we only have very rough algorithms for trying to do this. There's no really brilliant way to do it.
Okay.
But if it could do it, it would be amazing. I think we would love to use this architecture much more. So that's what people have been spending. Just the 1980s. Yeah, there's a huge effort in trying to understand how to figure out what this is. The said is the physicists have been spent 60, 70 years on this problem. And there's no great answer to that.
Thank you, Peter.